water itself goes through this reversible process, and this reversible process here in water, you'll notice, gives us hydroniums and hydroxides. And because it gives us hydroniums and hydroxides, we then have the pieces of acids and bases. Now, it turns out normal water, neutral water, has equal amounts of hydronium and hydroxide ions, and not a lot of the water goes through this. We'll get into this here in a moment, but not a lot of the water goes through this process. But when we add an acid or a base, we increase the amount of one of these, and it shifts the equilibrium. Acidic solutions have more hydronium than hydroxide, and vice versa for your basic solutions. This will eventually apply to the pH, how strong an acid or a base is. Strong and concentrate. We'll get into the difference there. Anyway, water is amphoteric, which simply means it can act as an acid or a base. There are other amphoteric substances, but water is our important one. In water, you end up with one hydrogen being transferred from one water molecule, and it gets transferred to the other one. Well, if we have something donating a hydrogen, that makes it a Bronsted-Lowry acid, which then forms its conjugate over here, the Bronsted-Lowry conjugate base, which has is what's formed when the hydrogen was donated. Over here we have the thing that accepted the hydrogen, so that is the base, and its matching piece on the other side is the conjugate acid. But water can behave both as an acid and base, and in the ionization of water, this actually happens where the water behaves as both at the same time. Anyway, this here is the same reaction. It's just labeled this time as the individual pieces there. In pure water, it turns out the concentrations of these two are equal and tiny. Just to emphasize this with scientific notation, we're talking 0.0000001 molar. And so very little of the water actually dissociates into hydronium and hydroxides. Anyway, we write that out in scientific notation as 1 times 10 to the negative 7th molar. Together, then, we come up with something we call the water constant. K for constant, subscript W for water here. The water constant is equal to the product of those two. So we're multiplying those two with one another. When you're multiplying powers of 10, you multiply the numbers in front. Well, 1 times 1 is 1, the negative 7s here, your powers you add together, and so negative 7 plus negative 7, we get negative 14. This is technically only at one temperature. Temperatures can cause Le Chatelier shifts as well, and it will change a little bit. We usually stick with imagining the problems and in the lab doing the reactions at this. The amount it shifts is negligible for your standard room temperatures, but really high quality, picky professional labs will get into actually doing those adjustments as necessary. Anyway, this here, this equation is going to be important as we get into doing pHs, the water constant formula here. Anyway, this kind of just goes through what we just described and what was listed in the bar chart earlier. This simply says that in acid, a hydronium is more common, and base hydroxide is more common. You know that already from our Arrhenius definition and Bronsted-Lowry definitions. Pure water is neutral. That's been mentioned already, so we're just going to keep moving here. Acidic solution, there you go. Hydronium more common. Basic solution, hydroxide more common. And so then the amount that is each of these changes. It's no longer the 10 to the negative 7th, and so you're getting smaller, bigger numbers in the decimal, but that means smaller the way we write them out because there's fewer zeros there leading the numbers in there. And there's that picture once again. Here is a list of them, and if you want to take a moment here, I'd encourage you to pause, take a moment to multiply these by one another, especially the ones where the numbers in front are 1s, and prove to yourself that it actually comes out to 1 times 10 to the negative 14th. But notice, this is always true. The concentration of hydrogen or hydronium times the concentration of hydroxide always equals 1 times 10 to the negative 14th, the water constant. Because of that, if we know 1 and we always know the water constant because it's a constant, then we can solve for the other. These two here are simply the algebra rearrangements of those two. To get something alone on one side, you divide by the other piece, and you divide both sides by that piece. It cancels out on one side, and you're left with this or this, depending on which of these two you're wanting to solve for. Take a moment and prove this to yourself algebraically if you don't follow the math that I just talked through there real quick. Anyway, keeping that in mind, and I went ahead and copied that over here and left it up here as a reminder for us. This one here asks us to calculate the H3O plus concentration if we know the OH concentration. So I'm going to start out actually with the this equation here rather than relying on this being rearranged already. Certainly you could do this, but I always go just start with the one formula. I only have to know the one formula, and then I can algebraically rearrange it to get to this one and solve my problem. So anyway here, we know that Kw is equal to the H3O plus concentration multiplied by the OH minus concentration, and we're given the OH minus concentration here. Personally, I like to insert the numbers rather than rearranging to get this one here first. I don't like to do math with letters. I can handle the algebra, but if I don't have to, I'll do as little of it as possible. So I like to plug in the 1 times 10 to the negative 14th here, and then we have the concentration of H3O plus that we want to solve for. If you want to change that to your more standard variable like you would in math, call that an X, you can. I have no problem handling other things as the variables. In fact, I had an algebra teacher who preferred to always use other letters, and so I kind of got used to doing algebra with other letters before I was forced to do algebra with just x's as our variable. Anyway, so now we have this. To get the hydronium here alone, we're going to divide both sides by 5 times 10 to the negative 8th. I suppose I was talking as I wrote this one out. This here is the hydroxide concentration, which of course I just got from the problem there. That's going to cancel out over here. We're going to divide by 5 times 10 to the negative 8th over here, and then I need a calculator. Cut out the I need a calculator through actually getting a calculator and doing the calculation. Anyway, at this point, I punch this into the calculator, and I get the concentration of H3O plus is equal to 2 times 10 should be 2.0, so that it matches this in terms of number of sig figs. You also I'll point out here that this also has 2 digits there, so my final answer is going to add 2 digits here, but 2 times 10 to the negative 7th molar. Side note, this here, the units on this are technically molar squared, so that when you do molar squared divided by molar, molar cancels out with one of the 2 molars there, and you're left with molar here for this. To be honest, if you dropped your units here and just remember that concentrations are in molar, it would be fine. The other thing, hopefully you know how to type scientific notation into your calculator properly. I believe there's a slide later on that specifically addresses that, so I'll wait until then. If there's not, if I've hidden that slide, then you can take a look at the PowerPoint version with all the slides there, or I will post another video that goes specifically into it. That's not one that you're required to watch, but if you don't know how to do it, you don't want to type this in as physically hitting the button times 10 caret to do the power at negative 8. It screws up order of operations when you do that, because scientific notation is a way to abbreviate how we write a number. It is not actually a multiplication operation, and so it changes how order of operations works. Anyway, here we're doing another problem just like that one, and so I'm going to just work this one out. I didn't bring my formula over here this time, but here this time we're given the H3O plus and we're asked to solve for the OH minus. If you go back and look at the formula, remember Kw is equal to the concentration of H3O plus times the concentration of OH minus. Now, I will work this one out the way that the textbook does, where I don't plug in the numbers first, but instead rearrange. Since we want to know what this one is, we need to get that one alone. To get that one alone, we're going to divide by both sides by the concentration of H3O plus. And then because of that, we're going to end up with Kw over concentration of H3O plus is equal to the concentration of OH minus, because these two here are going to cancel out. Now we can plug in the numbers. I'm just going to write it over here to the right. So Kw is 1 times 10 to the negative 14th. And the concentration of H3O plus we get from the problem up here, which is 2 times 10 to the negative 3. I'll point out I'm dropping the decimal zeros, but I'll still use them on my final answer when I go to come up with my sig figs. And now it's just punching into a calculator. And I get 5.0 times 10 to the negative 12th molar. Since this is a multiple choice problem, we can see that that is the same as that one there. One final practice from this, since I've shown twice how to rearrange this one, I'm just going to start with the already rearranged to save us a little bit of time here. But if we want to know the concentration of H3O plus, it is equal to 1 times 10 to the negative 14th divided by the concentration of OH minus, which in this case is 5 times 10 to the negative 8th. And then we plug it into a calculator. And I get 2 times 10 to the negative 7th molar. That's a negative 7 in the superscript there.